So good afternoon to one and all. Is the screen visible?
Yes, sir.
Yes, sir.
Okay. So in the previous class, we was already discussed about the different types of moving iron instruments. So there are mainly two types of moving iron instruments are there. One is attraction type, second one is which one?
Repulsion.
Repulsion type. Okay, repulsion type is again classified into two types. What are those types? Yes or no? Repulsion type moving iron instrument.
Coaxial.
Huh?
Radial or coaxial.
Radial type repulsion type moving iron instrument. Second one is coaxial type repulsion type moving iron instrument. So the working construction, working principle already we have discussed. The torque equation for the moving iron instrument, we are not considering this equation for the radial, repulsion, attraction. Commonly we are going to deriving this torque equation of moving iron instrument here. So for that reason, the title I have taken here is torque equation of moving iron instrument. Okay. Plus some parameters we'll discuss here now. Let the I we are going to consider, that is initial current here. So according to the principle, what will tell that one, I will take here now. We are providing some current here now starting, that is called initial current here. After that, if I increase it, that one means that change of current, that is called a DI. We are going to call that one here now. This is DI, this is I, and the total current is nothing but I plus, how much that is? I plus DI. Yes, this one. Here 0 is there. From 0 to I here now. I to this one is change of current we are considering here now. So the total current from here to here, that is called, how much it is? I plus DI. We can call that one. Yes or no? This is I plus DI. The total current is I plus DI here now. So the initial current we are considering as I here now. So the instrument has some inductance, that is called L, that is also initial inductance only we are considering here now. The deflection, how much deflection is occurred here now, and these three are the initial condition. I, L, theta. I is nothing but current, L is nothing but inductance, theta is nothing but deflection. If the current is changing, then the inductance will change. The flux will change. It means flux linkage will be changes, obviously. Then current change, it means the deflection will also changes over there. So IL here now, the change in or increase in current is called a DI. Change in deflection, that is called a D theta. Change in inductance, that is called a DL. We are going to consider here. We are going to consider here now. IL theta. Current, inductance, deflection here now. Next, change in current DI, change in deflection D theta, change in inductance, that is called DL. So these 6 letters, yeah, representation we are considering here now. Consider a small increment in the current supplied here now. Instead of this initial current, there is a small increment of the current supplied here now to the coil. Whatever to the coil we are going to supply the supply current, that is fixed coil we are going to use here now. So if I have increased a small increment in the supplied current of the instrument, due to this current, due to small increment, the deflection will changes. So that is the current, this current, let D theta be the deflection under deflecting torque here now. Because of this change in the current deflects the pointer here now. So under this deflecting torque, the deflection will occur, that is called D theta here. So due to such deflection, some mechanical work will be done here now. The pointer will be at here. So because of change in the current, the pointer will change its position. Yes or no? The pointer will change its position here now. So from here to here, the pointer is moving, means the mechanical work is done here now. The mechanical work is done here now. So from here to here, which torque is done here now? Deflecting torque. What is this one? This is called theta here now. So the total mechanical work done is nothing but deflecting torque into change in theta here now. Previously the change in theta was here. Because of changing the current, the deflection will change here now. So that changed deflection is d theta here we have considered here. So the mechanical work done is nothing but deflecting product of deflecting torque and change in deflection here now. So TD into d theta. This equation number we are considering as equation number 1. Equation number 1. If you have a pen and paper, you can write also this one. You want to take this one? At least to write equation 1 directly. See, simply listening is different, writing is different. 10 times reading is equal to 1 time writing. So if you have pen and paper, then you have to write in a pen and paper here now. So mechanical work equal to TD into d theta, that is called equation number 1. Consider that. So I will clear this all the things. Next I will go for the equation number 2 here now. Roll number 24. Now he is joining. So next, see, all the equations are related one to another. All the equations are related here now. Okay. So next here, in order to affect the increment of di in the current here now, increment, initial current se humne some current we have changed here now, initial current to some current we have changed here now. So some student has called for, because of that it was disconnected. So just a minute, I will share once again. Is it visible? The screen is visible?
Yes, sir.
Okay. So because of change in the current, increment in the current I to di, in that one, in the current, there must be increase in the applied voltage given by. So V equal to IR, we know the formula. V equal to IR. Okay, the current increase means the supply voltage will also increase. By increasing the supply voltage only we can increase the current. Yes. So for that reason, so there must be increase in the applied voltage given by here now. So that applied voltage is given by here E equal to, we are considering as applied voltage, E equal to, we are considering as applied voltage, the rate of change of inductance and current here now with respect to time. So dLi by dt we are considering here now with respect to time, the voltage changed here now. So change in inductance and current here now, actually the change in L di by d theta, actual formula is the inductance here now E equal to L di by dt. We have studied in the magnetic circuit already in the first year, L di by dt here now. But in this circuit, the inductance is also variable here now. It is variable thing here now. For that reason, dLi by dt we have considered here now. dLi and by dt here now. So both are varying here now. With respect to time, we have to differentiate here now. It is nothing but, I think, differentiation of UV or XY. I don't know which one you have studied here now. In the mathematics, you have studied that one. Differentiation of UV or XY. Anything. Which one you have studied?
UV.
UV. Okay. UV means I will erase this one, XY. Differentiation of UV here. No. UV, differentiation of UV. U dV by dt. Yes. U dV by dt plus V into du by dt. Yes, we have done like this only, na? This is the standard formula is there. The mathematics. U into dV by dt plus V into dV du by dt here now. So L is indicating as U, I we are considering as V here now. Anything we can consider here now. First one term you keep separate here now. I will keep separate here now. So L I am doing differentiation with respect to time plus Here I we have kept separate. Next what we have to do? L I will keep separate here. Now the current I am going to do the differentiation here. By doing this one, so I dl by dt plus L di by dt here now. So this one here I am considering as equation number 2 here now. Equation number 2 here now. This is called E here. This is called E here. It is nothing but applied voltage here now. So equation number 2 here. Both I and L are changing here now. For that reason we have done here. Okay. So the whatever the because of changing the current, whatever the mechanical work we have done, that equation we have written, and the applied voltage also we have written here now. Now we'll go for change of energy or energy stored in the circuit. We are going to. Yes. Someone is speaking. Want to ask anything? Rule number 26. Rupesh. Rupesh. Okay. So now the total supply applied voltage we have discussed here now. Now what we have to discuss, what is the energy supplied here now to that circuit here. The energy supplied is nothing but the energy formula we have to consider here now. Voltage current into time here. Now we can call that one here now. So the total energy supplied is the product of voltage and current with change in time or time increment, we can tell that one here. Or time increment here. We have voltage, current, or change in the current, the time or time increment here now. Initial time t and time increment we are going to consider as dt here now. Change in time. dt is nothing but change in time only we can call. Yes. dt equal to change in time. Please try to give the reply. At least you can tell yes, no, like that only. Then only I can feel that one I am explaining to you only. Otherwise it will feel like that one I am explaining to me only. So energy supplied equal to voltage into current into time increment. Voltage current into time increment. Rule number 2. What is the time now? Okay. Now here voltage means what? This is the voltage applied only. We have calculated E here. Yes.
Yes.
E. Current is nothing but I, and time increment is nothing but dt here now. So E into I into dt here now. We have written here now. EI dt here. EI dt here now. Just a minute. Equation rule number 4. Okay. So EI dt we have to consider. What is the equation here? Only E is there. So to derive the electric energy supplied here now, here only E is there. Here what is there? It is I dt. E into I dt is there. So from multiplying I dt into this equation, we'll get the energy supplied equation. Multiplying I dt into the equation number 2, will you get the energy supplied equation, complete equation in the form of L and I? Yes?
Yes, sir.
What we have to do? We have to multiply both sides of equation number 2 by I dt here now. I will multiply both sides of equation number 2. Both sides of equation number 2 by I dt here. We will get, so E is already there. I into dt I will multiply into LHS side. It is nothing but EI dt. It is of course. So whole equation I will write as it is into I dt. I have multiplied here. So EI dt equal to I dl by dt plus L di by dt into I dt. We have multiplied here. Now you expand the term here now. You enter, you split this equation into that terms, you split here now. What I will do here only, I will write here, somewhere I will write here now. So LHS you keep as it is EI dt. Here I is there, here I is there. It will become I square. Yes. I into I square.
Yes, sir.
So dl by dt into dt. dl by dt into dt is nothing but dt gets cancelled here. First I will write here now. I into I square dl by dt into dt here now. I will written here now. Plus as it is L into I, L into I, Li. So again di by dt, into dt here, into dt. Sorry, di by dt into dt here. Okay. Now you check here now by checking this one. Here dt gets cancelled. These two. Here also dt gets cancelled here. Yes.
Yes, sir.
So what is the term left here now? I square dl. Here li di. Li or il both are same only here now. So that is equation number 3 we are going to consider. This is energy supplied here now. We have calculated energy supplied here now. So the energy supplied ei dt equal to I square dl plus il di. That is equation number 3 I am going to consider here now. That is equation number 3 here now. So up to it is clear up to here. Equation 3 is very important. Equation 3, 4, 5. Then we are combining here now. Energy supplied, energy stored, and mechanical work. All we are going to consider. Energy supplied we have calculated here now. Next we have to calculate energy stored in the magnetic fields. So mechanical work is clear. To solve this electrical energy supplied, we have derived equation 2 and 3 here. We have derived equation 2 and 3. First we have derived voltage supplied. From this voltage supplied, we have derived the energy supplied to the circuit here. How much energy we have supplied here. Is it clear?
Yes, sir.
So you note equation number 3 here now. It is also important. Equation number 3, that is ei dt equal to I square dl plus il di. So equal to electrical energy supplied. You can write that one. Electrical energy supplied. Next, what we will do? Now we have to identify the stored energy. We have to identify here now. So assuming, just think that one. Assume that here now the energy stored in the electrical field is neglected. Electrical field means electrical, whatever the electric field is there in the conductor and all the things, that is neglected. But energy stored in the magnetic field we are considering here. So the electromagnetic effect only it is operating, moving iron instrument. Whatever the energy stored in the electrical field, that is neglecting, but the mechanical force will be produced because of the magnetic field only. So we are considering that the energy stored in the magnetic field as 1/2 Li square we are going to consider here. So for the initial condition, the energy stored in the magnetic field is 1/2 Li square here now. So this is initial energy stored here. When the current supplied only I supply here than a current, on that situation the energy stored in the magnetic field is 1/2 Li square. We are considering this one here. Next, when the current changes to di, on that condition the energy stored also changes from 1/2 Li square to 1/2 L plus dl. So to the what is the total current here now? I plus di we are going to call, na? I plus di. Like that, the total energy changes here now 1/2 L ka place mein L plus initial inductance plus change in the inductance here now. So L plus dl into the I we are going to consider I plus di is here, square is there, we have applied square here. We have applied the square here now. So the energy stored will also changes here now. So from this equation, what you can write, this one is the final value. This one is the final value of energy stored. This one is the initial value of the energy stored. So the net energy stored is how much we have to identify here. Net energy stored here now. I will tell that one. Suppose the initially 5 ampere current was there. Initially 5 ampere current was there. After some time I will change the current into 8 ampere. What is the net change of the current? Net change of the current, what is that one? What is the total change here now? How much it is changed? आपके पास पहला 100 रुपए रहते. Okay, so after 2 days you have 150 rupees. What is the change here now? कितना चेंज हो गए? I'm asking to you peoples only.
15 rupees increase.
50
rupees.
rupees.
So how you are calculating the change? 150 minus 100. So final value minus initial value.
Yes.
150 minus 100 is nothing but 50. Like that, the change in current is 8. 8 minus 5 it is. 8 minus 5 equal to 3 ampere. So total change is 3 ampere here now. Like that, the change in the energy storage is the final value minus initial value we have to do here now. So change in the stored energy is nothing but what we have calculated. The final value we'll write here now 1 by 2 L plus DL into I plus DI whole square. That is called A plus B whole square. What is the formula? A square plus 2AB plus B square.
Yes, sir.
So same thing we have written here now. 1 by 2 L plus DL I have kept as it is here now, plus this is A plus B whole square I have considered here now. So A is I square here now, I square plus 2I into DI plus DI square here now, minus what is the initial value? Initial energy stored is 1 by 2 Li square here now. Li square we have considered here now. So up to here, if you have any doubt, you can ask me here now. Idhar tak. Then you can simplify the equations. This is initial energy. This is after changing the current, the energy will also stored will change us here now. So the total change in the energy storage is nothing but final value minus initial value we are doing here now. By doing that one, we are going to get the equation. Up to here, any doubts? Up to here, any doubts?
No, sir.
Okay, so here what we have to do, the second order term we are going to neglect here. See here, second differentiation order term is there. Di we are going to neglect this one, neglect this one, and where is that one? One more after multiplication of this one, dl into di we are going to get. By neglecting here this term, neglect di square here. Now what I will do, will multiply here now. 1 by 2 into L into I square. We can do like this. This 1 by 2 into L into I square. The first term I have multiplied here. 1 by 2 I will multiply into here, and this whole is multiplied into here. I can write 1 by 2 Li square here. 1 by 2 Li square. Next 1 by 2 L, this one 1 by 2 L into 2I di by dt. 1 by 2 into 2 it will get cancelled here now. इसको लिखा तो समझ में आता है शायद आपको, है ना? और एक बार लिखने के बाद ही समझ में आ जाएगा. ठीक है, this term I will write here now. 1 by 2 where I will write here only. 1 by 2 L into 2 di, 2I into di. So this 2 and this 2 gets cancelled here. So IL into di, the left term here now. This 2 is multiplied into here now. Is multiplied into here. This is already first term we have considered here now. This one we have considered. So 1 by 2 L into 2I di, the left term is IL di is the left term. Yes?
Yes, sir.
Okay, next. Plus this one. This one is over now. Here 1 by 2 L into di square, but di square is already neglected. हमने neglect किए ये term, इसको multiply नहीं करने का. So as it is, these two are over now. Next what we have to do, next 1 by 2 dl into I square. These two we have to multiply into this, not this one. This is also over now here now. So 1 by 2 into dl into I square. Yes. 1 by 2 into dl into I square here. No, so 1 by 2 dl into I square we have written here. Plus symbol plus here. No, again 1 by 2 and into 2 gets cancelled here. No, so dl into di here. No, so I dl di is term will get here. No, again second differentiation will come here. No, d and d here. No, so this term also we are neglecting here. No, neglecting I di dl here. What is the term left here now? 1 by 2 li. I will take the color different. I'll remove all the things here. So you neglecting, I will mark that one. Neglecting this term, you neglect here now. We are going to neglect this term. Neglecting this ideal, 1 by 2 li square is there here. Okay, 1 by 2 li square plus il di plus 1 by 2 dl I square minus 1 by 2 li square. Same as it is, we have to write here. So here plus 1 by 2 li square is there. Here minus 1 by 2 li square is there. Both will get cancelled.
Yes, sir.
Plus 1 by 2 li square minus 1 by 2 li square, both will cancel here now. So il di plus 1 by 2 I square dl. This is the change in energy or change in stored energy here now. That is equation number 4 we are going to consider. This is the equation number 4, that is change in stored energy. Stored energy में कितना change हो गए, that one we have identified here. So first one is mechanical work done we have calculated. Second one is energy supplied we have calculated. The third one is change in stored energy we have calculated. That one we have given as equation number 4 here. Up to here, equation number 1, 2, 3, 4. Any doubts you can ask now only. If you have any doubts, you ask now only. Next, what I am going to do, I am going to combine this equation number 1, 3, 4 here now. So here only, now only it is. If you have any doubts here, rearranging the equation and all the things, you can ask now. Any doubts?
No, sir.
Okay. So next, what it, the energy supplied is nothing but the increase in stored energy here, plus the energy required for mechanical work here. So the total energy supplied we have to calculate here. The total energy supplied is equal to change in stored energy. Current change होने के बाद कितने energy change हो गए? Change in stored energy plus the mechanical work done here. How much the mechanical work was done over there? So to calculate this one, what is this equation number? I will tell here now. So electrical energy supplied is nothing but which equation number? It is nothing but equation number 3 here now. Yes, the electrical energy supplied is equation number 3. We have given equation number 3 only, na? Yes or no? EIDT equation identify किया हमने.
Yes, sir.
That is equation number 3. Change in stored energy, that is just now we have calculated, that is equation number 4 here now. Equation number 4. What is the mechanical work done equation? Equation number 1. Yes.
Yes, sir.
So combining these equation number 3, that is nothing but electrical energy supplied is equal to the summation of change in stored energy plus the mechanical work done is called as the electrical energy supplied. Here we are going to calculate. So equation number 3 you write down here now. I square dl plus idl by idl di here now. Il di I square dl plus il di. Equation number 4 here only it is there. Il di plus 1 by 2 I square dl. Il di plus 1 by 2 I square dl. Equation number 1 is nothing but the deflecting torque and change in the deflection, that is called Td into d theta here. Td into d theta we can use here now. So combining here now, see here, Anything it will cancel here, no? Can you check once again? Anything is cancelling here, no? LHS side, RHS side. Any terms get cancelled or not? You can tell me. Any terms will get cancelled? You also you have to involve in this one. Not understanding then. So listen carefully. Here I square DL plus IL DI is there equal to, here also IL DI is there. RHS side. Yes.
Yes, sir.
So when I will send into LHS side, it will become minus. The plus term will become minus here now. Next,
Yes.
1 by 2 I square DL is there. When I will send into LHS side, again this plus will become minus. Equal to RHS, I will keep as it is here. See here. Here plus ILDI is there. Here minus ILDI is there. Both will get cancelled here now. This term and this term plus ILDI minus ILDI. Yes.
Yes, sir.
Next, here 1 I square DL is there. Here minus 1 by 2 I square DL is there. So 1 minus 1 by 2. 1 by 2 I square DL we can write down. So you take common here now. I square DL here is our I square DL is there. Here also I square DL is there. You take common here no. 1 minus 1 by 2 we can write that one. 1 minus 1 by 2 is nothing but what? 1 minus 1 by 2. This is very terrible. You are not, I don't know, intentionally you are not giving the answer or you don't know answers.
1 by 2, sir.
1 by 2 only, no? 1 minus 1 by 2. 1 में half minus किया तो कितना बचते हैं? Half ही बचने वाला है ना? So that is 1 by 2 into I square DL here, no? TD d theta equal to 1 by 2 I square DL here, no? So same thing we have written here, no? TD d theta equal to 1 by 2 I square DL. I square by DL. From this one, can you tell me the deflecting torque equation formula? TD equal to 1 by 2, TD equal to 1 by 2, I square as it is, I square DL by d theta. Yes? Can write
Yes,
like
sir.
this?
Yes,
1
sir.
by 2 I square DL by d theta is our deflecting torque equation or the torque equation of moving iron instrument here. This is the final equation of the torque equation here. The torque equation of moving iron instrument is 1 by 2 I square DL by d theta here now. D theta. So you just imagine that one. This change of inductance is constant, change of deflection is constant. Then what is not this one? Later I will tell that one. Later I will tell that one here now. So this is TD. Already we know the controlling torque equal to K theta. We know the formula. Yes.
Yes.
Controlling torque KC TC equal to K theta here no. And we already know that. We already know the controlling torque equal to deflecting torque. TC equal to TD also we know the formula. Yes. Yes or
Yes,
no?
sir.
Controlling torque equal to deflecting torque. So TC equal to K theta is there. TC equal to K theta. And TD equal to 1 by 2 I square DL by d theta. So what is the formula for theta equal to? Here you send it K into this side here, no? Theta equal to 1 by 2 I square by K DL by d theta. We can write like this. Yes?
Yes, sir.
So from this equation, you consider these all are constant here, no? So theta is directly proportional to the I square, we can call that one. Theta is directly proportional to the I square. So here we have proved that one. The scale is not uniform here, no. The whatever the angle of deflection is directly proportional to the square of the current we have proved here. Now, thus the scale is not uniform here. Now, thus the deflection is proportional to the square of the current through the coil, and the instrument gives the square law response here. Now, this is indicates here. Now, so you have to mainly, while deriving the derivation of this one, equation number 1, 2, 3, 4, you have to remember that one. Then the final addition, you can do that one. So, but while solving the problem, this equation is very important, and this equation is very important here, or this one, these two. If you know this one, then TC equal to TD, you can use the formula here. So you can take the screenshot of this one, or if you have a pen and paper, you write this one. We will go for the numericals here. We'll go for the numericals here. If you have any doubts, you can ask now also. अभी भी कुछ doubt है इसमें? The TD we have derived. Later, all the equations procedure is same only, same previously whatever we have used for the PMMC and all the things. Someone is speaking. Nilesh Babar, yes. Babar Nilesh, anything you want to ask?
No, sir.
Okay. So all of you note down this formula: TD, TC, and TD equal to TC, or TC equal to TD. You note down this formula: TC equal to TD. You note down this formula. So it completes the torque equation of a moving iron instrument. So the moving iron instrument, it has some advantages and it also has some disadvantages here. Now, the disadvantage, we can tell that one, this is only the deflection is proportional to the square of the current also we can produce, but the torque and weight ratio is very high for this instrument. So even it is used for the application of this one, we can use this instrument for both AC and DC. That is very important and main disadvantage of the moving iron instrument. So I will display that slide also, advantages and disadvantages. So you this formula, as you remember, while solving the problems, you get that one. All of you have bring the calculator also. Take the calculators and sit down with calculator, pen, paper. I'll give the problem. Just I will explain the question. You have to solve by using these formulas only. This one, and this formula. ये तीनों formula use करके आप calculation करना पड़ेगा. It may be theta, it may be current, or it may be change in inductance or change in deflection, whatever it may be, or deflecting torque or controlling torque. These parameters only we are going to identify here. So the instrument, it has some advantages also. This can be used. The main advantage of the moving iron instrument is it can be used for both DC and AC measurement. We can use to this instrument for the voltage measurement, current measurement of AC as well as DC also. And it has the torque weight ratio is also high. So because of this very high torque, the errors will be less here now. The frictional errors will be less, we can call that one. So single type of moving element we can use here now. Some moving iron element we are using here now. For that reason, it can cover wide range, hence instrument are cheaper than other types. This instrument is cheaper than the PMMC, we can say that one here. So even whatever the moving iron is there, that it can carry the current carry होते क्या उसमें, inside that one, whatever the moving iron part is there. So it doesn't carry any currents over there. So there are no current carrying parts in the moving system. Hence these meters are extremely rugged or reliable operation it can give here. So they will give the actually good accuracy values also. They can give the 2% less errors are 2% less as compared to the PMMC, and they can withstand large loads also. So the range of instrument can be extended here also. By connecting the shunts and multipliers, we can extend the range here now. They can tell that one, the range can be extended by using some different techniques. We are going to call that one. So if any instrument or whatever you consider, it has some advantages, means it also has some disadvantages also. So this instrument also, it has some disadvantages. That is called, the first disadvantage is the scale is not uniform, because angle of deflection is directly proportional to the square of current here now. So there are serious issues, because in the hysteresis, frequency changes, stray magnetic field, because the moving magnet or iron we are using in between a magnetic field over there. So the hysteresis current will flow in the iron parts only. Leakages are there here now. So another thing is continuous operation, the temperature will increases. Then for the metal in the materials, the temperature increases means the resistance of that instrument will be also increases, which will be increase the resistance and decreases the stiffness of that spring control we are using, means that is stiffness will be reduces. So some errors may be occurs over there. So due to non-linear BH curve, we can, by doing that one, it is non-linear. So the square current is proportional here, no, not proportional exactly. So theta is not exactly proportional to the square of the current also, we are going to call that one. So I told that one, this instrument is used for both AC and DC here, no, but the calibration is different for AC and DC. So the same instrument, if we are going to use for the AC applications and DC applications separately, means the calibration we have to do separately. So these can be operate for the specific frequency, that is called 25 to 125 hertz frequency range. You can operate this one, and the power consumption is also very high for this instrument here. So it has some 7 advantages, some 6 disadvantages are also there here now. So this formula you remember, I'm telling once again, this formula you remember and note down the first formula here, first problem here. All of you note down the problem. All of you note down the problem. The change of inductance for a moving iron emitter is, the change of inductance here now, change of inductance for a moving iron emitter is 2 microhenry per degree, 2 microhenry per degree. The control spring constant is 5 into 10 to the power of -7 Newton meter per degree. Newton meter per degree. Newton meter per degree. So the maximum deflection of the pointer is 100 degree. Maximum deflection of the pointer is 100 degree. Then what is the current corresponding to maximum deflection here now? What is the current corresponding to maximum deflection here now? This one you have to do the calculation here. This one you have to do the calculation. Read the question carefully here now. Read the question carefully. Anyone, if you want to explain this one, what are the given data? Can you tell anyone? Any one of you, you can tell the given data.
Yes, sir.
Tell me.
Control spring constant is given.
Which one?
Control spring constant 5 into 10 to -7 Newton meter.
Which one that
per
is?
degree.
That is called K, na? Control spring constant means
Yes,
which
sir.
one? Okay, K is given. Next. I will write here K equal to, given here, no? K equal to, otherwise directly I will mark here only. This is equal to K. Next. Next, what is this one? 100 degree.
Deflection pointer.
Deflecting torque.
Deflecting torque. Maximum deflection of pointer is 100 degree. Means
D theta.
d theta. D theta is nothing but what? Change in theta हो गया. D theta is nothing but, this is not a d theta. Think about that one. Maximum deflection they are telling here now. So here 0 is there. Here the scale is there. The maximum deflection is here, pointer is there here now. What is this one? From here to here. What is that? That is called theta. Maximum deflection is nothing but theta. We are going to call that one. So the 100 degree is theta. So here K is given. Here theta is given. K theta. What is the formula for that one? Which formula it is? Nothing but K theta equal to which formula it is? K theta equal to
1/2 I squared dl by d theta.
okay, you are going direct last answers equation. Okay, no problem. Here K is given, theta is given. Can you tell me what is this one? This one, change of inductance. That one, change of inductance for a moving iron emitter is, that is 2 microhenry per degree. What is this one? 2 microhenry per degree. What is that? This one, what is that? Microhenry means Henry. What is the unit here now?
Inductance.
Inductance. What is the word he has used?
dl
here?
by d theta.
Change of
dl by d
inductance
theta.
is nothing but dl. Per degree is nothing but, that is called d theta. Yes. So first all of you
Yes, sir.
write the given data as dl by d theta. dl by d theta equal to dl by d theta equal to the given, that is called 2 into 10 to the power of minus 6. 2 into 10 to the power of minus 6 here now. Yes. Next, the K is given. You write the formula for K, that is called K equal to 5 into 10 to the power of minus 7. 5 into 10 to the power of minus 7. The unit you can write here now. You have to write Newton meter per degree, that is Henry per degree. Next, theta equal to how much he has given? 100. They have given here now, 100 degree. Yes, these three parameters they have given here now. Already you know the formula. You know the formula TC equal to TD. TC equal to TD formula मालूम है सबको? Yes.
Yes, sir.
So TC equal to K theta is there. TC equal to K theta and TD equal to 1 by 2 I square dl by d theta. dl by d theta here now. K is given value. Yes.
Yes, sir.
Theta is given.
Yes,
1
sir.
by 2 is value here now. I square we have to calculate here. dl by d theta also given here now. So from this equation you can write the formula for I square equal to k theta or 2k theta. This 1 by 2 when I will send into LHS side, it will become 2. 1 by 2 is nothing but 2 here now, divided by dl by d theta. Yes. dl by d theta here now. Substitute the value. 2 into 5 into this one 100. 2 into 5 into 100 and into 10 to the power of minus 6 here now, divided by, sorry, minus 7. This 2 you can consider here now. 2 into k is nothing but 5 into 10 to the power of minus 7 into 10 to the power of minus 7. What is the theta? Theta equal to 100. Yes, theta equal to 100 divided by dl by d theta is nothing but 2 into 10 to the power of minus 6 here now. 2 into 10 to the power of minus 6 here. Yes.
50.
50. 2 gets cancelled here now. 10 to the power of minus 6 and 10 to the power of here minus 7 is there. When you'll send upper side, it will become plus 6. So minus 1 is left here now. So this 10 to the power of minus 1 and 1 0 also we can cancel here now. 5 into 10 it is nothing but 5 into 10? 50 only, na? 50 here now.
Yes, sir.
So what is this one? What is the question here now? What is the current corresponding to maximum deflection here now? Current corresponding to maximum deflection, that is called 50 square here now. Square of the current is there here now. Next, I equal to square root of 50. How much it is? Nothing but I equal to square root of 50. How much it is?
7.07.
Just 7.07 ampere here now. This is the current corresponding to maximum deflection. So this is the one example I have solved as it is here now. You didn't solve this one. With explanation I have solved. For detail in the printed value you want means I will show that one also. In the printed value we have displayed here now. So see the answer of that printed value as seen from the article here now. They have mentioned here all the things, details here now. So is it clear? Any doubts you have? You now only you ask me. I will explain this one. I'm ready to explain if you have a doubt. The next problem I will not tell anything. I will just read the question and I will sit down. You have to solve that one. If you have any doubts here, you can ask now only. For that reason only, given data is very important. While writing the given data itself, it is very important. If the given data is correct, then apply the formula. If substituting is important. Next, that is not a difficult thing. Only the thing is given data. While writing the given data is the difficult part. Is it clear? Will you solve the next problem? Same type of problem I will give, but instead of I can give theta or k calculation. Will you solve? Any doubts?
Yes, sir.
Okay. Take this problem and solve yourself here now. The inductance of attraction type instrument is given by the inductance of attraction type instrument is given by L equal to 10 plus 5 theta minus theta square microhenry where theta is the deflection in radian. Theta is the deflection in radian from zero position. The spring constant is 12 into 10 to the power of minus 6 Newton meter per radian. Find out the deflection for a current of 5 ampere. Here he has given current, he has given the spring constant, but you have to calculate theta here. L is also given. Theta you have to calculate here. So you take this one for the homework. All of you solve this problem. So I will ask in the next class. I will ask this one. Okay, all of you solve this one. Can I close this one? PPT.
1 minute.
Okay, you note it down. So here L is given, K is given, I is given. You have to identify the theta. You have to identify. Very simple problem is there. Already theta formula directly it is there. 1 by 2 I square by k dl by d theta. So everything is given. Just last formula may substitute kiya na, you'll get the answer of that. Can I close now? So we'll stop here only and we'll continue in the next class. I will end the meeting. Can I?
Yes, sir.